Here's a very interesting solid mechanics question, which for a change, it doesn't actually use beams or cantilever beams or pin jointed frames or anything like that. It's a bit more different and it looks at creating sort of a half bridge with books. Okay. And this is the kind of question that a first year student doing some form of engineering might encounter. So if you'd like to see anything similar to this, let me know down in the comments. So for this question, we have to figure out what is the longest distance between, so, okay, we consider that we have three books. And the question is, what's the maximum distance between the leftmost edge of the bottom book and the rightmost edge of the top book? Okay, in other words, what's this A plus well, the question is asking for this, but you can also find, if you're interested, that distance between the left and the right. So let's try to understand how we would approach this. So what I would recommend is starting from the top, okay? And the reason you might want to start from the top is because there are fewer forces, okay? There's nothing sitting on the top book, meaning that we can easily represent what's going on. So first of all, we know that one of the forces acting on the top book is the weight, right? That's the weight W, like this. And in addition to the weight, we have the normal force. Again, here's the key to this question. Normally, if this book was sitting on a horizontal surface, right, the normal force would be in the center, right? Because we say that the weight would be uniform, or the book would be homogeneous, maybe. So the normal force would be acting in the center. But in this case, we're actually looking at what's happening in the limiting scenario. Okay, and what I mean by that is we're looking at what happens just before or just when the book starts toppling over, and it will topple over clockwise. Okay, so if you look at this drawing here, when this book will start rotating, all that normal force, all that reaction force with the second book will occur here, like this. Okay, because if you think about it, what happens is that the second book looks like this, and as the top book starts to rotate, then what actually happens is something like that, right? So as the top book starts rotating clockwise, because it's a rigid object, all that normal force is going to be concentrated at that corner here, okay? So all the normal force basically is just going to be focused at that particular point, okay? And we have to find, where should this be? We want to find where is this location so that that distance that we're interested in is maximized. Okay, so here's how we will do this. We're gonna assume that we don't actually know how much to the right of the second book the top book is. Okay, so I'm gonna say that I don't know if the top book should be like this, or if it should be like this. So can we get away with this instead? Okay, which one? Preferably we want this one, because this one will give us the longest distance, but is this actually feasible? Okay, so I'm gonna assume that we don't actually know where this corner is going to be. Okay, so as a result, I'm just going to place that normal force in a random location. Okay, so I'm just gonna say that the corner is going to be here. Okay, without any loss of generality, of course. So I'll say that the distance from, let's use a different color, the distance from here to here, I'm gonna call this x1, okay? And I want to find what x1 is. So clearly I can make the top and the middle books look like this, okay? But is this actually going to give me the highest horizontal distance? and that's what we have to now check. So let's do some force balances. Okay, so in this case, we only have two forces acting on the top book. We have the weight of it, which is acting in the middle. Okay, assuming that the books are homogeneous, which generally is not really the case. But we'll assume the weight is acting in the middle and the normal force is acting at some distance x1. Okay, so what I'll do is I will take moments about this point here, which I'll call O. Okay, now we will take moments about O as follows. So let's say that the sum of moments about O is going to be equal to 0. Okay, and it has to be 0 because this is an equilibrium problem. We want our stack of books to stay still, okay, and we don't want any angular accelerations to happen. So when we take moments about point O, I'm going to say that any counterclockwise moment is positive. So this is what we have. We have a moment due to force N, which is N times x1. And then we have the moment due to W. Okay, and just as a reminder, the distance from here to the line of action of W is just A over 2. Okay, because we know that the length of one book is A. So we have that N times x1 and then minus W times A over 2, right? It's minus because this is a clockwise moment about point O. Yeah, you can convince yourself that's the case. So we want x1 as high as possible, basically. So this is going to give us that if we rearrange. So x1 is going to be a over 2 multiplied by w over n. Okay, a is fixed, so we can't actually mess around with this because this is the length of the book, and the weight of the book is the same as the weight of any other book. So this is a constant. So what we then have to check is what exactly is the n here. And to figure this out, we will take that the sum of forces in the y direction has to be 0 because there should be no rotation, but there should be no translation either. And there are only two forces here. There's W, which is acting down. So we have minus W plus N equals 0. So N is equal to W. Okay? So we have x1 is equal to a over 2 times w over w. So x1 is a over 2. And it turns out this is actually the maximum value of x1. Okay, it's also quite intuitive. And this is saying that for the normal force to be on the corner, right? So just when the book starts when the top book starts toppling over, that distance has to be the same as a over 2. In other words, the top book looks like this. So you've got a here, and then you have another a here, like this. Okay, so you've got the weight acting like that, and the weight is equal to the normal force. So when the top book just starts to rotate, the normal force is acting on the same line of action as W. Okay, so we found that the maximum distance here is a over 2. Okay, so we figured out what's happening with the top book. So let's move on to the middle one. So with the middle book, the situation is a bit more complicated because there are a few more forces going on. So let's actually figure out the free body diagram for the middle book. So we have weight, which is acting down like this. We have the normal force from the top book, right, which is acting essentially here. So it's acting on the edge of the middle book, and that's going to be pushing down. So that force is going to look like this. Okay, and we know that this is also W. Okay, and in addition to that, we have another force due to the fact that the second book is sitting on another book, right? So when or just before equilibrium is broken, the normal force from the middle book is going to shift to wherever the edge of the bottom book is. Okay, so this is where this is what we're going to look at. So we now have to figure out what this distance is, which will give us the highest possible distance that we can arrange our book bridge in. Okay, so like before, I'm going to say that, okay, my normal force, I'm going to put it somewhere here. Right, let me just erase this because this is just W. Okay, so this is W and this is, let's call it N prime perhaps. And I'm saying that I don't actually know what this distance is. Okay, so I'm going to call this X2. And those are all the forces acting on the middle book. Okay, we have the weight of it, we have the normal force from the book above it, and we have the normal force which comes from the book underneath. So now we can write the following. So we have n prime minus w is equal to 0. So for equilibrium, we must have that this normal force n prime should be equal to 2w, which shouldn't really be surprising because this is a statics problem. Okay, there's no vertical acceleration anyway. Now the other thing is, what is this x2? What's the maximum value of x2? Okay, and to do that, we're going to take moments. You can take moments about any point, but I'm going to take moments about this point here, which I'm going to call O again. So the sum of moments about O equals 0, and as usual counterclockwise is positive. So this is what we have. We've got n prime multiplied by x2, right? This is my counterclockwise moment, and then we have minus w times a over 2. So now I'm looking at this w, and then I have minus w times a, so that's the moment arm of this green w, okay? And this should be equal to 0. Additionally, we also have that n prime is 2w, so I'm going to substitute n prime for 2w. So this is going to be 2w x2 minus, and I can combine this into one thing. So this is going to be minus w times 3a over 2 equals 0. Okay, and as you can see, we can cancel out w's, which is nice. So what we'll get is that x2 will be, so if you rearrange this, you'll get that x2 is 3a over 4. So let's have a quick look at what this actually means. So this n prime will be acting halfway between the weight and between the blue force and the red force, basically. Okay, so this is 2w right here, and this makes sense, right? Because first of all, we must have a value of n prime, which is the sum of those two forces, but it must also act in the middle, so there's no balance, right? So if you take moments about this point, you should get that the moment of w, um, which is this force, which is the actual weight, should equal the moment of this other w. Okay, so the only way in which this makes sense is if n prime is acting at 3a over 4. So this is 3a over 4. Okay, so what we then have is, well, we pretty much figured out everything we need. So let's draw our bridge, which now contains all the information that we need. So we have the book at the top. So there's a distance a over 2 to the right of the middle book, and then we have this here. So there's 3/4 of the bottom book underneath the second book. Okay, and that's it. So now we know that this here is a. Okay, this is the length of the book. This here is a over 4, right? Because from here to here you got 3a over 4, which means that this total distance from here to here, which is the maximum distance that you can arrange the books along until they fall, is going to be equal to a over 4 plus a over 2, and it's going to be equal to 3a over 4. And that's the answer. That's the final answer, and that's the end of the question.